Okay, good morning, everybody. I hope my audio is better now than last time. But okay, first things first, I hope you had the time to look over your graded free response part of test number 2. I just realized that the deadline for regrading requests is today. So if you haven't done so, kindly take a look at your free response part of the test. If you have any questions on how it was graded, or you feel that you should have gotten more points out of a certain problem, then just let me know. The deadline is today. So you have, I guess, until midnight tonight to send me your request. Just don't forget to attach the actual PDF file of your test together with the original file name as you downloaded it. So send it to me via email or via chat here in MS Teams, so that I can take a look at it. I'll review it. Yeah. Also, kindly describe your question in details. So I'll take a look at it, evaluate it, and make the proper recommendations. So as of yesterday, I received 2 regrading requests, and I already replied to those emails. So if you are one of those people who submitted regrading request, then kindly check your emails. I replied to you already. Okay. And then for today, I made a poll asking whether you want to go through some more examples of trig sub. And I guess I have 6 responses here, 5 of which says, yeah, let's do some more trig examples. But before I go there, just let me know what were you able to finish in the lecture today. So I know that the plan is to finish 8.4 and probably start with 8.5 this week. So are you done doing partial fraction decomposition? I guess that's 8.4.
Yeah, we just finished it today.
Okay, good. So if you just finished it today, and then you haven't started with 8.5 yet?
She did like a quick overview of things that we should review for 8.5, but we're gonna start on Friday.
Okay, yeah. So I guess that puts us in a good situation or in a good place, even if we devote the first 20 minutes of the class today for some more examples about trig substitution. Okay. So what about trig substitution? I know that the process is long, but I hope the premise and the process is clear to you guys. There are 3 general cases that we will consider for trigonometric substitution. That is, whenever your integral has radicals of the form a squared minus x squared, a squared plus x squared, and x squared minus a squared. And depending on which of these 3 cases occur in your integrand, then you need to do the proper trigonometric substitution, whereby you change the variable x into a trigonometric function. And why do we do that? We do that so that the radical will be gone, because we will rely on the Pythagorean identities that will turn the binomial inside the square root to simply be a squared monomial, right? So here, if you have a squared minus x squared, the motivating identity is, sine squared theta plus cosine squared theta equals 1. That's why you can choose x to be a sine theta. If you do the substitution, you see that the radicand will simply be a cosine theta after a lot of trigonometry, some algebraic manipulations, right? So again, this is the only new part here, distinguishing what type of trig function to introduce into your function. But after you do so, you will be left with another integral, probably with powers of trig functions, and that will require you to use some techniques that you have learned from section 8.3, which is how to integrate powers of trig functions, right? And I guess the main reaction from you guys last time is that the process is a little bit straightforward, but the actual implementation is very long, right? So you just need to be careful and remember what are the trigonometric identities at your disposal and what are the techniques that you can use when dealing with this very whenever there are combinations of powers of trig functions. But of course, I suggest that you do this as a last resort, meaning you try use substitution first. Perhaps that will work, but otherwise, yeah, just go ahead and do the trig substitution. Okay, so let me just browse through what we did last time because I honestly forgot already. So we did this basic example. You had a question from the quiz. Went over this. Okay. Oh, we just had 2 examples? I thought we had more. Okay, but anyway, let's try some more new one. I have here some examples that are not from the worksheet, so probably it's a good thing so that you can work on these problems on your own. So let me do this. Okay. Unless you have some specific problems from the quiz or from your homework that you want to go over with. But while waiting for that, I'll start with this first problem. So we want to evaluate, let me call this problem 1. I'll use red ink for the number so that just as a legend that this is not coming from the exercises from above. So the first problem is to integrate x to the 5th all over 36x squared plus 1 to the 3/2 from 0 to 1/6. Let me just double check if this is similar to what we did last time. Hold on. Okay, a bit similar. Okay, but I guess this would be a nice review of what we need to do. Okay. All right. So whenever dealing with definite integrals, that you expect that a lot of substitutions will be going on for the integral, just like for this example, you might want to discard or to ignore the bounds first and consider the indefinite integral first, so that you won't be taken points off if you forgot to change one of the bounds. Okay, let me do that. And then I'll just use the fundamental theorem of calculus later once I get an antiderivative for the integrand. Okay, so here, if you let u to be equal to 36x squared plus 1, that means you will need a 72x out of your integral. And actually, that's not easy to find because you have an x to the 5th in the numerator. So you can take an x out of it. You'll have an x to the 4th left if you'll try u substitution. But you will be left with with also a complicated expression if you do that. I guess it can be done. I'll bait some algebraic manipulation. But to illustrate trig sub, so I'm going to do trig sub here. And you look at the one that has a radical. Of course, there are no radicals here at first glance. But if you notice that the exponent here is 3/2, there's a denominator 2 in the exponent. So that means there's a radical hidden somewhere here, right? And that would be the integral, the square root of 36x squared plus 1 raised to the 3rd power. So basically this, you can treat this as a radicand. And if you compare it with the basic cases that we have from above, that means here, I guess we want 36x squared to be replaced by tangent squared theta, right? So that we can take advantage of the identity 1 plus tangent squared x equals secant squared x. That's the motivating identity here, right? So if you cannot determine the right substitution or what are the constants that should go in front of your substitution, you can do it this way. Compare what you want. So I want the 36x squared to be expressed in terms of a tangent. So that's how I got this, right? And I want to do that so that the radical will be tangent squared theta plus 1. right? And I can write that in terms of a secant, right? So, okay. And then now I will solve for the proper substitute here. So that means 6x must be equal to tangent theta, right? After you take the square root of both sides, you assume that everything is positive, so that's good. So that means the substitution you're using actually is x equals 1/6 of tangent theta. Okay, and that means dx is equal to 1/6 secant squared theta d theta. Okay, so now this integral that we have over here can be rewritten in terms of the variable theta. So x to the fifth will be replaced by 1 over 6 to the fifth of tangent to the fifth theta. All right, because x is 1/6 tangent theta, so you raise both sides here to the fifth power, so you get the numerator, and then here we'll have well, 36x squared will be equal to tangent squared theta plus 1 raised to the 3/2, and then dx is 1/6 secant squared theta d theta. All right. So now we change everything in terms of the variable theta. If you're dealing with the definite integral, ultra resolution, then you would have a different set of bounds here. You cannot write 0 to 1/6 anymore because those are bounds for x. Now your variable here is theta, so the bounds here should be bounds for theta. So you need to plug in x equals 0 here and solve for what is the new value for theta. Then for the upper bound, you plug in x equals 1/6 over here, then you compute for theta. And you see how complicated that would be, because then you will need to use arctangents in your bounds. And I don't want to do that at this point, so I'll consider the indefinite integral first. Okay? And then once you perform that substitution, basically this is the entire, this is what trigonometric substitution tells us to do. The rest of the thing will be algebraic manipulation and using previous integration techniques. So let's try to simplify. So here I'll have 1/6 to the 6th power outside, right? Because I have a 1/6 to the 5th here. I have a 1/6 there, so they multiply out to 1/6 to the 6th. And that can go out of the integral. Then I'll have tangent to the 5th theta, secant squared theta, all over. Secant squared theta plus 1 is simply secant squared theta, right? Using the motivating identity. Okay. And then the reason why we want to have a perfect square, a perfect monomial square in the denominator is so that this squared, exponent 2 will cancel with the square root there, right? So basically what we'll have is tangent to the 5th theta, secant squared theta, all over secant cubed theta, d theta. All right. And now I don't need to worry about the absolute value bars because x's go from 0 to 1/6, and from 0 to 1/6, that means tangent is positive. So that means we are on the first quadrant. So that's why I knew that x's and then the tangents and the secants will all be positive because we are simply living on the first quadrant. Okay, so no need to worry about the absolute value bars. So we have this expression here. Then let's try to simplify further. So I have 1 over 6 to the 6th integral of tangent to the 5th theta all over secant theta d theta. And here you see we have a case of rational function of trig expressions, right? So we'll try to see how we can deal with this. We cannot apply things from section 8.3 yet because that only concerns products of powers of trig functions. So I guess here we need to rely on some basic trig identities first to try to see how we can write it in a simpler way. Note that tangent to the 5th can be written as sine to the 5th theta over cosine to the 5th theta, right? That's a basic rational identity. But the secant here can be written as 1 over cosine putting the cosine in the numerator, right? So you had the 1 over secant theta. So you can use reciprocal identities to write it as cosine theta, okay? So ultimately here we see that the given expression is simply sine to the 5th theta over cosine to the 4th theta d theta. And what do you think we can do here? Well, as we have learned from powers of trig functions, here I have an odd power for sine. I can isolate one of those signs and reserve that for the du, so that I can let u be equal to cosine to the 4th theta. Yes, Herson, you're correct. I'm gonna do u sub here, but before doing the u sub, I'll make a necessary preparation here, because here you see you will be planning to let u to be equal to cosine theta, right? So that the denominator will be nicer looking, right? But that will require du equal to negative sine theta d theta. So I should prepare a sine theta for the du. So I'll have a sine to the 4th theta here. Then I'll have a cosine to the 4th theta in the denominator. Then I'll set aside the sine theta d theta and prepare that for the u substitution. So in this particular case, I'm going to let u to be equal to cosine theta coming from the denominator, because remember, our prime suspect for the u substitution would be the denominator. And that's what I did here. Du will be negative sine theta d theta, which is what I planned. That's why I isolated the sine theta there. But remember, we'll have a problem on top, a little bit of a problem, because we have sine to the 4th. So, but since its exponent is even, I can use the Pythagorean identity to turn it in terms of a cosine. So essentially, this would be 1 over 6 to the 6. So this would be 1 minus cosine squared theta, quantity squared. I hope you got that, guys. Basically, what I did here first is to imagine sine to the 4th, sine squared theta, quantity squared, right? And I know that sine squared theta can be written as 1 minus cosine squared theta all over cosine to the 4th theta, sine theta d theta. And now at this point, I can perform the u sub. So this will just be 1 minus u squared, quantity squared, over u to the 4th times negative du. Right? And then now I'll put the minus sign outside, 1 over 6 to the 6th. And this would be 1 minus 2u squared plus u to the 4th all over u to the 4th du. Then this would be minus 1 over 6 to the 6th. I'll perform the division 1 by 1. So we'll have u to the minus 4 minus 2u to the minus 2 plus 1 du. Right? And then now we can integrate. This would be u to the negative 3 over negative 3 minus 2u to the minus 1 over minus 1 plus u plus the arbitrary constant c, because we're doing indefinite integral over here. Okay, then let's just rewrite it in another way. I'll have negative 1 over 6 to the 6 times negative 1 over 3 u cubed plus 2 over u plus the arbitrary constant c. All right. And then now I guess we can go back to the original variable, or not the original, but revert to the previous variable. So we have u, but we knew that u stands for cosine theta. So we'll have minus 1 over 3 cosine cubed theta plus 2 over cosine theta plus cosine theta plus the arbitrary constant c. And now we still need to go back to the original variable, okay? So the original variable is x, and for that, let's draw a triangle over here. Let's say the right angle is there. Let's put theta over here. And let's recall what was our trig sub here. We let, remember, we let x be equal to 1/6 tangent theta, right? That was our substitution. Or we can write it as 6x equals tangent theta, okay? And remember from your SOHCAHTOA, tangent is opposite over adjacent. So that means I can imagine 6x as 6x over 1. So that means opposite theta should be 6x. Adjacent to theta should be equal to 1. And the hypotenuse using the Pythagorean identity should be 36x squared plus 1. Okay? And from here, we can compute, maybe I should put that here in the middle. Oops. Okay. Then so from here, we can deduce that cosine theta being adjacent over hypotenuse would be 1 over root of 36x squared plus 1. Okay, are you still with me, guys? I hope everything makes sense. All good? All right, and then now we can move on and plug this back in. So we'll have -1 over 6 to the 6th of -1 over 3 cosine cubed. So cosine is 1 over 36x squared plus 1 to the 3rd power plus 2 over 1 over 36x squared plus 1 plus 1 over root of 36x squared plus 1 plus the arbitrary constant c. I guess you can write it in a better way as -1 over 6 to the 6 times negative, I guess this would be 36x squared plus 1 raised to the 3/2 all over 3 plus twice root of 36x squared plus 1 plus 1 over root of 36x squared plus 1 plus c. Okay? And now we have the antiderivative in terms of the variable x. So we can say that the original integral, which is definite, so it's going to be 0 to 1/6 of x to the 5th over 36x squared plus 1 dx will be equal to this guy. Is one thing I like about online classes. I have this copy-paste mechanisms with me. Something I cannot do with a face-to-face class. Imagine writing everything in the chalkboard. Yeah, whenever dealing with very long expressions. So here we evaluated from 0 to 1 over 6th. Okay. And if you'll do the calculations, I guess I'll leave the details to you guys. You just need to plug in 1/6 and 0, then subtract them from each other. I guess what you will obtain is 1 over 17,496 minus 11 root 2 over 279936. Those are big numbers. But if this was in the exam, then you can leave your answer like 1 over 6 to the 6th. No need to evaluate what 6 to the 6th is. But yeah, I pre-calculated it using Mathematica earlier, so I got this nice simplified expressions. But again, if it was in an exam and you are dealing with large numbers, you can leave it in terms of exponentials or in terms of unsimplified numbers. So, but at least you need to plug in the 1/6 and plug in the 0 just to let us know that that you know that you need to plug in those bounds. Josh, in the exams, I hope you don't have to deal with very large numbers. It's just that I didn't expect this example to involve very large numbers, but I don't think you will be tested in working with very large numbers. Those are just arithmetic stuff. So yeah, the bounds could be simpler. And yeah, at least you should be expected to perform the process, but not the numbers, the big numbers themselves. You can leave them as 6 to the 6 or 6 to the 6 times 5 or something like that. Okay. Any other comments or questions? That took a while. I didn't expect it to go that long. Maybe I'll give one more example, but I will leave the details to you guys. Okay. Any other comments? Yeah, that's a good question, Arsalan. So hopefully you won't have to deal with such a long expression like this. Based on experience, sometimes you will just be asked in a multiple choice problem in the exam about what is the right substitution. So if you will be given the integral and what should be your trig sub for x? Is it a tangent theta, a secant theta, or something like that? But of course, I don't think you will be asked to do something this long in the exam. All right, so this is just for you to practice. Oh, Josh, you can do it. I think you can do it. But it's just your first year doing this stuff, so that's why it seems to be very difficult or hard. But believe me, if you'll be doing calculus for 10 years or 15 years like what I have done, then these things would seem natural. Actually, even for me who have done calculus for a decade or so, this is still long for me. So yeah. But the good thing is we do have the internet and we do have good calculating software, so you can double check your answer. Let's try this one, though I'll just outline the solution and leave the details to you guys. So if you have, say, the integral of x cubed root of 4 minus 9x squared, if I am to make the exam, to write the examination for you guys, I wouldn't ask you to solve a problem using trig sub because the process is long. Basically, just the substitution itself is long enough. So what I'll probably ask you to do is to give me the right the right trigonometric substitution to be used, and then move on. Go to the next question, right? So let's see, what would be the proper trigonometric substitution for this? Well, first you take, you'll check if u sub will work. Obviously, I don't think it will. So the next thing is to try u substitution. Here, this is your radical. And if you compare it with one of the forms we have earlier, it seems that we should let x to involve the sine function, right? So that we can use the identity 1 minus sine squared equals cosine squared, right? But what do I want to be expressed in terms of the sine function? So here I want 9x squared to become 4 sine squared theta, right? That's what I want to happen. This thing 9x squared should be 4 sine squared theta, so that what will happen somewhere in my solution is that I'll have something here times the square root of 4 minus 4 sine squared theta. And then this would be something root of 4 times 1 minus sine squared theta. And here we'll have cosine squared theta. Then you take the square root, so you'll simply have a 2 cosine theta out of that radical, right? So that's the plan. So if that is the case, then we want 9x squared to be equal to 4 sine squared theta. We need to force the issue that entire 9x squared in the subtrahend inside the radical should be equal to 4 sine squared theta. And that's what we will start our solution with. So this is our goal. Let me just erase these things, okay? So if we take the square root of both sides and assuming that the roots are positive, then we'll have this, okay? And that tells me that we should replace x by 2/3 sine of theta, okay? And then if that is the case, then dx will be 2/3 cosine theta d theta, all right? And then we use the substitutions in here, x cubed, so that's going to be 2/3 sine theta quantity cubed. And then we know what will happen here. We'll have 4 sine squared theta for 4 minus 9x squared. And then dx will be replaced by, 2/3 cosine theta d theta. All right. So this would be what? 2/3 to the 4th sine cubed theta cosine theta times, this would be 4 times 1 minus sine squared theta d theta. And we'll have 2/3 to the 4th outside of the integral. We'll have sine cubed theta cosine theta, and then this would be 4 cosine squared theta as what we expected. All right. And this would be 2/3 to the 4th integral of sine to the 3rd theta cosine theta times 2 cosine theta d theta. And so we'll have this. Maybe I'll take the 2 out. So I'll have 2 to the 5th over 3 to the 4th. Then I'll have sine cubed theta cosine squared theta d theta. Okay? And that's basically what trig substitution will give us. This would be the simplest form. Okay? Now, what do you think should be done next? So here you need to borrow techniques from section 8.3. I guess somebody wants to answer. Yes, person, that's correct. You're going to use trig powers. And how exactly will you apply trig powers here? So here the key is to isolate one of the signs because you have an odd power of sign. So take away one of those signs and reserve that for your du, right? Yeah, that's correct, Herson. So I'll have sine squared theta, cosine squared theta, sine theta, d theta. So this is what we'll reserve for the du, okay? And if that is du, then u presumably will be cosine theta. And the good thing about that is I can rewrite the first factor as cosine squared theta using the Pythagorean identity. And now we're ready for the u sub. So here we're gonna let u be equal to cosine theta. And du, as what we planned, would be negative sine theta d theta. And so this would be negative 2 to the 5th, 3 to the 4th, times 1 minus u squared times u squared times du, which is basically negative 2 to the 5th over 3 to the 4th of u squared minus u to the 4th du. Then we integrate negative 2 to the 5th over 3/4 or 3 to the 4th times u to the 3rd over 3 minus u to the 5th over 5 plus arbitrary constant c. And then now we need to revert to the variable to the variable x. So you draw your triangle again. Say the angle, the 90-degree angle is here. Let's put theta over here. And then let's recall our substitution statement. Remember, we let x be equal to 2/3 of sine theta. So that means we are letting sine theta to be equal to 3x over 2. Okay. And from SOHCAHTOA, sine is opposite over hypotenuse. So opposite theta should be 3x units. The hypotenuse should be 2 units. Okay. And so by Pythagorean identity, the third leg would be 4 minus 9x squared, which is the original radical that we started with. So that tells me my setup probably is correct because I recovered what we started with, right? Okay, so now we just need to plug these things in. So I'll have negative 2 to the fifth over 3 to the fourth times u cubed. Oh, I forgot what to revert to theta. What is u? U is cosine. So that would be cosine cubed theta over 3 minus cosine to the fifth theta all over 5 plus the arbitrary constant c. But remember from SOHCAHTOA, cosine is adjacent over hypotenuse. So adjacent to theta is this side, and this is the hypotenuse. So that means this will just be 4 minus 9x squared. That's adjacent over hypotenuse to the third power times the 1/3 that it originally had, minus 1/5 cosine to the fifth. So that would be 4 minus 9x squared all over 2 raised to the fifth power plus the arbitrary constant c. All right. So I guess that's not too hard. It's long, right? I agree, but I hope this is straightforward. Okay. And I hope I have illustrated the process of computing what should be or what's the proper trig substitution, because I guess probably you will be asked that in the exam. If you will not be asked to solve an entire trig sub problem, then at least you will be asked what would be the right trigonometric substitution. All right. What do you mean, Josh? You don't agree that you will just be you will not be asked to do an entire trig sub problem? Yeah, for a quiz, maybe not. Or were you already asking a quiz to do 10 of this for a quiz? Though a quiz have an hour, so you have more time there. But yeah, again, if I will be writing the exam, but I will not be the one writing the exam. But if it was up to me, then I'll just give you this integral and ask you what is the u substitution, and you should be able to tell me that x should be equal to 2/3 sine theta. And I hope I have illustrated the process of how to do that. All right. So yeah, now I guess it's all up to you. Try to practice and solve as many problems as possible. I know that might be difficult, but yeah, take little steps, but try to answer problems. And that's the only way that you get used to this type of long solutions. Okay. Now, is it good if we go to partial fraction decomposition now? Or you still have some lingering questions about trig sub? Again, my hope is that it will now be, it is now clearer how to do the process, at least the process. I know that the implementation of the method is another thing. It's quite long. You might need other techniques inside of that thing, but I hope that the methodology or the process is clear to you guys. Okay, so let's go to partial fraction decomposition. I already uploaded a blank version of worksheet 11. So you can look at it on my website. But again, basically, these are just the exercises from the textbook. And then we'll just pick some of them to answer. And then I'll leave the others to you guys. Okay, so for partial fraction decomposition, I guess it's easy. It's also easy to spot which integrals will require partial fraction decomposition. The thing here is that you are integrating a polynomial over a polynomial, or in general, a rational function that can be expressed in terms of a polynomial over a polynomial. Okay. So if that's the case, the first thing to check is make sure that the degree of the denominator is larger than the degree in the numerator. Okay. So before doing anything else, before doing the partial fraction decomposition, make sure that the degree of the denominator is strictly larger than the degree in the numerator. Because otherwise, oops, do long division first. Long division first. And I think it's a while since you have done long division. But that's the first thing, because partial fraction decomposition won't always work if the degree of the top is greater than or equal to the degree in the denominator. Okay. But assuming that you have already done this, that the degree of the bottom is greater than the degree of the top, then we do the partial fraction decomposition. So what do we mean by that? Well, what you'll need to do is to factor the denominator. So that's another pre-cal or algebra thing that you need to remember how to do. So you need to factor the denominator. So say we have this, and we have a bunch of factors over here. Okay. And what we want to do, as the name implies, we will be writing it in terms of partial fractions. So you have one big fraction here. We'll split it up into different pieces. So here we'll have a fraction plus another fraction plus another fraction plus another fraction, and so on until we get an expression equal to the right-hand side. So that's why it's called partial fraction decomposition. We have one fraction, we will split it up into the partial fractions. And the idea here is that it should be easier to integrate each of the partial fractions, because when we will be able to write the entire the original fraction in terms of a sum of little fractions, then the idea is hopefully those little fractions are okay. But there's a challenge here, how to do the partial fraction decomposition. Well, for that, it depends on the cases, right? So case one is that there are no repeated factors, no repeated factors. If there are no repeated factors, then the thing is that if you have, say, if you have, say, Q1, for instance, the first factor is degree, say it's degree n, then you will have a degree n minus 1 in the numerator all over Q1. So each non-repeated factor will get one fraction for it, okay, on the decomposition. So you copy the factor in the denominator, but the numerator will be a generic polynomial of degree 1 less than the degree of Q1. So say if Q1 is linear, then the numerator would be a generic constant. If Q1 is quadratic, then the numerator would be a generic linear function. If Q1 is cubic, then the numerator will be degree 2, and so on. Okay, so that's when you have no repeated factors. But the second case is that there are repeated factors, which again will entail a very long solution. Say Q1 is repeated, is degree, say, capital N, and repeated m times. Okay, So if Q1 is degree n and it is repeated capital M times, then there would be m fractions that will correspond to Q1. Q1, 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 and there should be m of them. And they would be in increasing powers. So you have Q1 here, then Q1 squared, Q2 cube, until you reach Qm minus 1. So if it's repeated 4 times, then there would be 3 fractions that will correspond to Q1, with denominators Q1, Q1 squared, and Q1 cubed. But their numerators will be a generic polynomial of degree n minus 1. So it will depend only on the original degree of Q1. So say if Q1, so maybe it's easier to give an example here. Say if Q1 is x plus 1 quantity squared, for instance. So it is degree 1 repeated twice. Then in the partial fraction decomposition, it will have 2 pieces. Okay. It will have 2 pieces, x plus 1 and x plus 1 squared. Sorry, this should be m, not m minus 1. Okay. So it will repeat until you get the same number of times it is repeated in the original expression. And then the numerator would be 1 degree less than the original factor. So the original factor here is linear, just repeated twice. So the numerators here would be generic constants. Okay. And then the hope is that each of these terms will be easy to integrate. I guess that's quite a lot to take in. Maybe I'll start with a quick example. And we only have 3 minutes left. Hopefully you don't mind if I take two minutes more than scheduled. So let's see. Let me try problem 17 first, and then we'll work with some more of the more interesting stuff on Friday. Okay. So let's try this. Okay. So we'll start with partial fraction decomposition. So we want to decompose 7 over x minus 2 times x plus 5. Lucky us, the denominator is already factored. The degree of the numerator is 0 because it's a constant. The degree of the denominator is 2. So definitely the bottom has a larger degree. So partial fraction decomposition should work well. What are the factors? We have x minus 2 and x plus 5. Nothing is repeated. Both of them are linear. So the fact that nothing is repeated, then both of them will get 1 fraction in the decomposition. All right. And then x minus 2 numerator would be a constant, a generic constant. Remember, it should be 1 degree less. So this is degree 1. So the numerator should be degree 0, which is a constant. And then same thing for x plus 5. It's non-repeated. It's linear, so it goes with a constant b on top. Okay, good so far? All right. And then now, what we have here is, okay, I can write it as a times x plus 5 plus b times x minus 2, because I need to solve for a and b, what exactly those constants are. Okay. So I'll basically write it this way. Okay. So if I were to perform the addition on the right-hand side, I'll get this. Okay. And note that this guy should be equal with this. Okay. But they do have the same denominators. So if they are equal, then the numerators must be equal to each other. All right. So I hope that's easy to accept. Basically, what you can do is to multiply both sides by the denominator, or simply disregard the denominators. because for those two fractions to be equal, since they already have equal denominators, then their numerators should match. And this should be true for all x's. So the fact that this equation must be true for all x's will allow us to choose specific x's that will help us to get the proper value for a and b. Okay. Now, what would be the nice choices for x? Theoretically, you can choose any value for x that you want, but you will see that it would be helpful if I will take x to be equal to, say, -5. Because if x is -5, plug in x equals -5 to this equation, you'll get 7 equals, oh, I'll have a times 0. And that's exactly why I chose x to be -5. And then so that a will disappear, leaving us only with -5 minus 2 over here. So that means 7 is equal to -7b. So b is equal to 1. Okay, and then now, how do we find a? Again, theoretically, you can pick any value of x you want, but I guess it will be more helpful if we will let x to be equal to 2. Anyway, this is true for any x, so it must be true for x equals 2. So that means we'll have 7 equals a times 7 plus b times 0. Okay, so that means 7 equals 7a, so a is also equal to 1. So therefore, the original integral, I forgot what the integral is. So that's 7 over x minus 2 times x plus 5 is equal to, hold on, okay. Integral of 1 over x minus 2. Oh, sorry, b should be -1. Is that correct? Did somebody got that? Yeah, you're correct, Harrison. Yeah, I just realized that b must be equal to -1. That would be -1 over x plus 5 dx. And then here you can we can integrate term by term, right? So integral of 1 over x minus 2 is ln of the absolute value of x minus 2 plus minus the integral of 1 over x plus 5 is ln of the absolute value of x plus 5 plus the arbitrary constant c. And you see that these two pieces in the partial fraction decomposition prove to be much easier to integrate than the original fraction. And the thing there is because the denominators of those pieces will definitely be of lesser degree than the original denominator. And that's the thing, or that's what we are hoping for in partial fraction decomposition. So that's how you do it. Let's try some more problems on Friday. But before that, I hope you will find some time to practice decomposing a certain fraction into partial fractions so that we can focus more on the integration next time. Or actually scrap that, because I think the integration are simple here, because what we will get out of the partial fraction decomposition are, I guess, more straightforward to integrate. The main crux of this method would be on finding the partial fraction decomposition properly. So we started with a basic example today. On Friday, let's try what happens when there are quadratic functions in the decomposition, if there are repeated factors and so on. Okay. So, but again, I hope you'll come with some questions on Friday so that we can discuss them, and hopefully that will help you in your quizzes. All right. And again, guys, take a look at your exams and let me know by midnight tonight if you have some questions. All right. Okay, guys, have a nice day. Bye, and see you on Friday.